Okay, let's see what we've got here. Minimum operations to convert all elements to zero, medium. You're given an array nums of size n consisting of non-negative integers, 0 or positive. You're tasked to supply some possibly zero operations on the array so that all elements become zero. In one operation, you can select a subarray I, j, where 0 less than equal to I, less than equal to j, less than n. Okay, so I and j are in order indexing. And set all occurrences of the minimum non-negative integer in that subarray to 0. Okay. Interesting. So set everything that's the min to 0 in the subarray. Return the minimum number of operations to make all elements in this. I'm missing something here. Wouldn't it just be the frequency of the different numbers, the count of the frequencies? Like you set all the 1s to 0, the 2s to 0. Okay, so it's 1. Return the minimum number of operations. This is 3 because you set the 1s to 0. Set the 2 to 0 and set this 3 to 0. Why is this 4? So you set all the 1s to 0. Oh, there's no 0 in the subarray? Yeah, I see. I think it's the minimum non-negative integer. Why can't you select 2 to 2? Ah, yeah. You can't select 2 to 2 because then this 0 gets in the way, right? Okay, you can't select the subarray that has 0 already. Otherwise, that's already the min. So you select everything. Well, you select only here, so it doesn't make a difference. So that's 1, and then 2, 3, 4. Could you have not chosen all the ones? Because that wouldn't really make sense, right? That'd be like 6, maybe. So you choose. Interesting. So it's almost like you're making islands, kinda. Every time you choose a subarray, all the min locations become 0, so therefore they cannot be used in any future subarray. Interesting. How would this go? 10 to the 5th. Definitely feels like this should probably be linear. Possibly n log n. It definitely shouldn't be n squared. Time complexity wise. Alright, let's do a random one here. Let's say it's pi 314 2 3 1 2 1. So you'd make it into the ones. So it'd be 1 4 2 3 2 and 3. And then you make the 3 4 3 3. And then you make those. So it's like one subarray, 2 3, and then 4 5 6 7 subarrays. Let's double check this. So this returns, I'm gonna guess 7. 3, 1, 4, 2, 3, 1, 1, 2, 1, 3. Do. Okay, with 7, yeah. What interesting. So I mean, I could do something where, what are the values in this array? Is it just random? Randomish, yep. Could do something where I map each number to its rank. So the minimum number becomes 1, the second lowest number becomes 2. That would require me compiling the list of all values, sorting them, and then doing some sort of exchange of value to rank. That would make this algorithm at least n log n. But it feels like that's probably better than trying to on the fly figure out the rank of a number within the next set of values. So I'm going to consider converting values to rank, i.e. Find set of all values, sort, determine rank of each value, and do replacement of value to rank. It's not really an IE, it's more like what you do. Okay, so that given if that's done, then basically I'm dealing with the nums array that is 1 to the number of values, so it's just not sporadic. So the first pass would have to be converting the 1s to 0, and then converting the 2s to 0, 3, 4, and onwards. Converting the 1s to 0. Converting 1s to 0. So if I do a pass, so if I do a 3, this 3 will be part of a subarray that contains the next 3, as long as there is no in-between value that is a 1 or 2, because a 1 or 2 between those 3's would prevent it from being part of the same subarray, because the 1's would need to become 0's first. Actually, is that correct? Yeah, I think that's right. Yeah, okay. I was thinking maybe you can somehow do the reverse and try to figure out the max and make it 0 first. But yeah, so the 3 would only be part of the same subarray if there's no 1 or 2 between them. Similarly, like the 4 would, let's go with another 4. Let's say that there's 2 4's here, that's fine. They're going to be part of the same subarray because there's no 1, 2, or 3 between them. The 1's don't care because there's nothing that's smaller than them that's going to be between them. Okay. So I do 3. see a 1. I know that 3 is going to be distinct. I see a 4. See a 2. See a 3. Number of operations. So I see a 3, I see a blank. Then that means there's going to be an operation for that 3. So maybe I can say this 3 is going to require an operation. And then I see a 4. How do I say that these two 4s, if they exist here? Guess I didn't copy this correctly. How could I say that these two 4s only count as one subarray? What's the logic there? So 2 so close, so close. 2 counts as another subarray if there's no 1 before it. There's no 1 between it and the prior 2. So I can say there's 3 here. And then when I see the next 3, I either need to know that there's been a 1 or 2 between those two 3s. And if there is, then there's going to be a different subarray. If I see a 4 here, I can say that there's no 1, 2, or 3 between this and the prior 4. So can I keep track of the minimum value? If I keep track of the index, keep track of the index of the last 1, the last 2, the last 3. Then if there exists something smaller than 3, I can keep track of the minimum between this and the last one. The minimum. So close. 4, 4. What am I tracking? What am I tracking? 3, 1. Or the smallest between this and the last 4. Three. This might be a monotonic stack. 3. I keep a monotonic decreasing stack. I keep 3, I keep 1. And the 4 clears the stack. 4 clears the stack. So what if I don't clear the stack? So let's say it's 3, 2, 1, 1, 2, 3. So in theory, this would require 1, 2, 3, 4, 5, 5 subarrays. So you keep 3 on the stack, 2 on the stack, 1 on the stack, 1, and then when you see the 2, what do? You see on the stack there's 1s already. So you know that this 2 is going to require another one. It's going to require another subarray. Right. So the 1's here. So keep a monotonic decreasing stack. You see the 2, you get rid of the 1's. Now, you get rid of the 1's, then you see another 2. How do you know that this 2 wasn't connected? Maybe you keep a stack of the value in the index, because you can't just have this be like confused with like a 322 deal. So I think you have to keep a value index maybe. And if you do that, then this 2 gets off the stack. And then you see a 3. And this 3, doesn't combine with this 3. You need to pop the 2. And then would pop 3. Each time you pop those, each time you pop the what happened? You add a subarray. You add a subarray to get that value. Okay, what I really should be thinking is like 1, 2, 3, 3, 2, 1. In theory, this would take 3 subarrays. So if you did a monotonic stack here, what would you do? Like, are you getting rid of 1, 2, and 3 as immediately as you see it? 1, 2, 3. Maybe you're keeping a monotonic increasing stack rather than decreasing stack. Yeah, 1, 2, 3, 3. Keeping a monotonic increasing. So the 2 would need to get rid of 3's here. And that'd be 1. And then these 2 would get rid of those, and that'd be another 1. Okay, it looks like a monotonic increasing stack. So here, monotonic increasing would require that 3 pops when you see a 2, so that's one array. Pops when you see a 1, that's another subarray. And then 1, 1, 2, 3. And at the end you do 3 gets 1, 2 gets 1, 1 gets 1. Okay, yeah. Stack. We're popping values off. stack is equivalent to creating subarrays. Okay. Okay, so let's go ahead and say values is equal to the set of nums. I want to convert the values to a list. And I guess maybe make that sorted. Sort in increasing order, yeah. And then convert those, convert them into rank. How to do efficiently convert into rank? Well, I could make a dictionary. Could make a dictionary. I wonder if there's a better way. Convert to list. I guess I could also sort twice, maybe. Sort. Values sort. Rank is the dictionary. And then for every index and range of values. Actually, now that I think about it, I guess I don't need this. This could have worked without converting it to ranks. It was just easier for me to figure out that, but this is not necessary. Okay, actually, that makes it a lot simpler. Increasing stack is going to be empty. N is equal to length of nums for each index in range n. Actually, do I even need the indexing? Don't need the indexing, to be honest. So value, for every value in nums, while, so whenever you do monotonic stack, you always ensure the kind of what was that term, like intrinsic value, not intrinsic value, the invariant. Yeah, the invariant property. You always ensure that the invariant property will be maintained, which is in this case the values are increasing once you add or append this value to the stack. So this would require that I remove from the stack anything that's smaller than this current value. So while the stack exists and the last item in the stack is bigger than the current value, then I need to add this value to the stack, or I need to remove it from the stack. and increment the answer number of operations. And I'm going to do one thing here, and I'm only going to add the item if it's not a duplicate of the top of the stack. If not increasing stack, so nothing's there, or increasing stack, the last item doesn't equal the current value, then append the value. Okay, so that should work until the very end, where it has like 1, 1, 2, 3, and then I need to just pop stuff up. I guess the number of items in the stack at that point should be unique and the same number of things that need to pop off. So I think I just return answer plus the size of the stack. Okay, I did that wrong for 0, 2. 0, 2 doesn't require operation with a 0. So I think what I can do, zeros never require operations. So if the value is 0, then I think I need to skip it. Doesn't seem right. So if the value is 0, then that 0 will always be there at the end. I think maybe I can make the increasing stack always have 0 here. And that would prevent it from ever requiring that I check this condition, because the dummy value of 0 is never going to get removed. It's always going to be smaller. And no 0 is added again. So I think it's going to be minus 1 here. Okay. I think I need to have a few more test cases just to make sure that this, nothing stupid like a bunch of zeros doesn't somehow trip it. Okay. I think this is, yeah, I think this is fine. Yeah. Cool beans, cool beans. Okay, well, that was interesting. Guess that was appropriately medium. So summary here, this is going to be this part ended up being unneeded, but could have been useful in some applications. Anyways, summary. So the consider the case of an array that is 1, 1, 1, 1, 2, 3, 3, 2, 1, something like that. The number of operations there would be 3 to make it into 0 array. Make 3's then 2s, then 1s into 0s. That array can somewhat easily be determined to have a monotonic increasing array as a way to track when to create new subarrays. So so the stack would initially have 1, 1, 2, 3. Those are none. Those are not decreasing. Actually, it would probably have maybe 1, 1. Actually, I'm going to modify this 1, 1, 2, or 1, 2, 3. When it sees the second 3, it will ignore, as that can be combined into the same subarray with the last 3. When it sees the 2, the second 2, it must pop the 3, which indicates that the bigger values between the 2's can be grouped into the same subarray. So the 3's would be one subarray eventually, but the 2's currently are in a bigger subarray that eventually will allow the 3's to be a smaller subarray. Similarly, when the second one is seen, the 2's can be interpreted as being part of an inner subarray. Each pop off the stack indicates an inner subarray. Finally, when done, the stack should one, one, two, three. 3 pops off. 2 pops off. 1. Yeah. Finally, when done, the stack should have the same number of unique values as required subarrays. This can be an example if array is strictly 1, 2, 3. That is the ending stack, and that matches the number, and the length matches the number of subarrays. Final note: to deal with possible zeros in the subarray, create the monotonic stack with a dummy 0. Only pop if the value is, or only append if the value does not match the last value in the array, in the stack. and um, and add length of the stack minus 1 at the end, because there's going to be 1, 0 in the stack. Time complexity, this can be O of n, as it does a single pass through the array to determine a number of operations. Space complexity, this just could also be O of n to maintain the monotonic stack, which could have size proportional or equal to the number of elements